Let's review some organic chemistry basics. 1. Alkanes have only single bonds. Because they cannot take on any additional atoms, alkanes are saturated hydrocarbons. 2. Alkenes have at least one carbon-carbon double bond. Alkynes have at least one carbon-carbon triple bond. Aromatic compounds are based on the benzene molecule, C6H6. Because alkenes, alkynes, and aromatic compounds can take on additional atoms, they are unsaturated. And 3, structural isomers have the same molecular formula, but have atoms with different bonding arrangements. Straight chain compounds have a single carbon backbone. And on the right, I've given you several representations of the exact same straight chain molecule. We can write this in any number of ways. I've got my shorthand zigzag notation where each endpoint indicates a carbon atom, so we have 5 endpoints, and then it's understood that each carbon has 4 bonds, and any bonds that aren't shown are understood to be connected to hydrogen atoms. Branched chain compounds have a main carbon backbone and one or more branches. So you can see the shorthand notation for this molecule. This is clearly a branched chain compound. If we wanted to figure out how many carbon atoms, we would simply count the endpoints of these straight lines. So let's go ahead and do that. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 carbon atoms, and how many hydrogens do we have? Every endpoint has to have 4 bonds, and any bonds that aren't shown are understood to be connected to hydrogens. So if I represent the hydrogens here with red dots, we would see that on this end we've got 3 hydrogens there. This intersection has 2. This end has 3. This intersection, there's a carbon atom right there. It's holding 1, 2, 3, and then the 4th hand has to be holding this hydrogen right here. If we count all those up, that gives us 18 hydrogens. Again, we don't draw the dots whenever we write this shorthand notation, but I put them in there so that you can start to understand what you're looking at. Substituted compounds, as the term would suggest, have one or more hydrogen atoms removed with other atoms in their place or places. Often substituted compounds have halogens. There are other substituent groups, as they're called. Halogens is a very common one, and if we were to figure out how many atoms of each type we have in this molecule in the lower right, I'm counting 11 hydrogens there, and there they are. The order that we put these atoms isn't really all that significant. Usually I put carbon first and then hydrogen and then alphabetically after that, but it really doesn't matter. But we certainly have 5 carbons, 1 bromine, and 11 hydrogens in that molecule. Branches and H-replacing atoms or groups are collectively called substituents. You can see here I've represented polyvinyl chloride with this model, and you can see that some hydrogen atoms have been taken off and replaced with chlorine atoms. A functional group is a characteristic pattern that makes up a portion of a larger molecule. Functional groups have specific atoms and specific bonding arrangements. The importance of functional groups is that they largely determine the behavior of their molecules. Just as an introduction, 3 functional groups that we could list here are the alcohols, the ketones, and the carboxylic acids. The alcohol functional group is OH, and you can see that the O is hanging on to, this would be some kind of carbon, a carbon atom and whatever is attached to that carbon atom. Ketone has a carbon atom with a double bond to an oxygen, and then carbon atom on the left and carbon on the right. the shorthand notation for a ketone would be written like that. A carboxylic acid has that functional group shape. The shorthand would look like that, and sometimes whenever you see these formulas written out, you see at the end of the molecule COOH, and that is indicating the carboxylic acid functional group. So there are many functional groups. Here are three of them. All alcohols, let's say, tend to behave similarly. All carboxylic acids tend to behave similarly. So we kind of group these into convenient categories so that we can better understand and see patterns in reactions. Many organic compounds are combinations of several of the categories we've just listed. For example, this compound here, for one thing, it's an alkene because it has a double bond, but it's also a substituted hydrocarbon because we've substituted a bromine in place of a hydrogen. I'm going to abbreviate that sub instead of just saying substituted because I don't want to write out the word substituted. This molecule is an alkane because it has only single bonds. It's substituted because we have a chlorine atom there, where normally we would think of a hydrogen atom being there, but this is clearly substituted. And it's also branched. You can see that there's a fork right here on the left side of the molecule. That molecule is branched and it's substituted. What about this molecule down here? It's substituted. We have a chlorine on this end, so that's a substituted compound. It's also got the alcohol functional group. This molecule has a functional group and it's substituted. Here again you can see that many organic compounds are combinations of some of these things. Let's do two more examples. This one here is the carboxylic acid functional group, and that's it. There's no branching in that molecule. There's no other substitutions made. What about this one? On the left side we see a fork, so this is a branched compound. In the middle here we have this structure, which hopefully you remember from the last slide, indicates a ketone. In other words, that's a functional group. And we have bromine substituted for hydrogen. So I'm seeing this as branched, and it has a functional group, and it's substituted. All three. Later on, we'll learn how to name all of these different compounds. But for today, that's it.